So, welcome everyone. In this lecture, we will look at another architecture that is often used in the modern deep learning or machine learning paradigms, which is called the transformer. Okay. Last time we started with multi-layer perceptrons or full feed-forward neural networks, and then we looked at convolutional neural networks. We also in the last session we looked at recurrent neural networks which were the architectures designed for sequence data processing. Now, continuing from there, we will look at another set of architectures called transformers that are based on this idea called attention mechanism. We will look at what attention mechanism is, and then I will look at transformers. In fact, most of the models today, including the large language models, are primarily driven by this architecture, the transformer architecture. Now, before we dive deeper into what the transformer architecture is, I want you to understand or appreciate a couple of ideas. See, if you recall the way we looked at kernel SVMs, which is that we started by saying that the data is separable and there exists a linear decision boundary, linear separability, and then we extended that idea to the cases where there is no linear separability. Okay. Now, what was the basic idea there? The idea was to project the data onto some other space, okay, and hope or assume that the data will become linearly separable in that space. Okay. Now, this idea of projecting the data, I mean, we have been doing this since a long time, right? We have been, even when we looked at the generalized linear regression, we said that the data that is not linearly separable or not explainable by a linear model can be linearized with a transform. Right. So, there is some data, you transform it into some other space, and you expect different behavior post transformation is what we have been seeing. So, what is the idea? Start with data X. So, you start with data space and learn a transformation, okay, phi to another space Z, okay, and then you learn your hypothesis or functions on Z. This was one thing that we have been doing, correct? Now, this kind of transformation of data from one space to the other, okay, is typically referred to as representations or embeddings. So, start from some space which is the given random variable, and then make your data undergo a transformation phi, and you get you project your data onto some other space typically represented by this variable Z, and call that the representation or the embedding and so on. We have already done this, remember. We had this phi to be a fixed transformation where it can be a polynomial projection or some other projection, and in the case of SVMs or kernel machines, we saw that this phi can be different transformations. We looked at Gaussian transformations and the RBF kernels and so on. Okay. Now, so far in most of the cases that we have seen, this phi, which is the function that transforms data from one space to the other, has been fixed and user defined. I also gave you examples from the classical signal processing community for this, right. Fourier transform, for instance, is one such embedding learning. So, given some data, you transform it into some other domain. Okay. All the classical transformations, the Fourier transform, Z transform, etc., are actually learning this sort of a representation. Now, if you carefully look at what we did with neural networks, okay, we had a composite function. So, we said h of x for a neural network was started with some transformation, and then there is another transformation and so on. So, this is what we said a neural network is. Now, this entire function, right, the entire operation can be seen as some nonlinear projection of data from one space to the other, isn't it? In fact, each of because neural network is a composite function, every inner function can be seen as one projection of data. So, W1x is one projection of data, okay, and then you have W2 times that projection. You project that projection onto some other space and so on, you keep doing this. So, every composition that we do can be seen as embedding learning. In that sense, a deep neural network is learning embeddings in a hierarchical manner. So, every layer of the neural network will give you a projection or an embedding of data. Do you see why? Because I mean, what is an embedding? It is basically some function of data, some projection of data onto some other space. Then you start from the data space, and the first layer of the neural network is some projection, and from there project that onto a second layer, onto a third layer, and so on. So, that way every layer in a deep neural network can be seen as some embedding that we are learning onto the data. Do you see this? Okay. In fact, what is done is, in some of the applications you train a neural network, let us say for some task. Let us say that you train a neural network for a classification task. What one can do is, during inference you take the data point, okay, pass it through the neural network, you tap the output of the neural network from some intermediate layer and use that as a representation of data, and you can build another classifier on top of those vectors. So, this is what is called as embedding learning. So, given a pre-trained neural network, as it is called, right, trained for some, I mean, what do you mean by pre-trained neural network? You have some neural network and there is a ERM that we have done. So, once we do the ERM, you can use that neural network and use this neural network to get projections of data by tapping onto the intermediate representations from the neural network. Do you see what I am saying? Yeah. Okay. This is also called representations or embeddings. Any composite function for that matter can be seen as, especially the neural network, can be seen as hierarchical representation or embedding learning. Okay. Now, the difference between let us say a kernel machine or an SVM and the neural network is that in classical frameworks such as transforms or even SVMs, we fix the transformation. But in a neural network, the transformation, the function that transforms the data is learned, and that depends on these parameters, isn't it? So, that way a neural network can be seen as a nonlinear basis, change of basis with learnable transformations. That is why it is powerful. I mean, instead of, what is the difference between, let us say, a Fourier transform and a deep neural network is that in Fourier transform you fix your basis onto which you project your data. In a neural network, the basis that is projecting, the basis onto which the data is being projected is being learned, okay, through parameters. Why am I saying this? Is because most of the architectural changes or designs that we do is an attempt towards learning a better embedding or a better representation, isn't it? Because all architectures or all neural networks now can be seen from this lens that you are learning a projection of data. So, any change that we do to the architecture is learning a projection onto the data. Does it make sense? I mean, we need this world view because it's very easy to see a transformer from this angle, that all we are trying to do is to learn a particular type of a projection or an embedding such that some behaviors are imposed. So, now connect this with our earlier discussion on Bayesian learning as well. Every choice that we make on the architecture, okay, is a certain type of regularization that we are doing, which in turn impacts what sort of projection are we learning on the data. Okay, that is what we are doing, right. Okay. So, now let us look at this idea called attention mechanism. I will just give you an overview of this and then I will mathematically define this. The idea of attention is as follows. Now, recall that if you have sequential data where the input is sequence and output is a sequence, okay, we saw how to handle the sequence to sequence task using recurrent neural networks. Remember that? So, how did we do that? Suppose we have an input sequence x1, x2 up to xt, okay. So, we had these recurrent neural networks, recurrent cells as we call it, RNN cells, and then we tap the output in an autoregressive manner. This was y1, y2 up to yt dash. See, note that t and t dash are different, meaning the length of the input and the output sequence need not be the same. And because we are doing a parameter sharing across time, this is not an issue at all. We can easily do that. Okay. So, this is what we saw, and what was this? This was ht, the tth latent representation or tth hidden state. And last class, a student made a very interesting comment that all the information about the input sequence is now being enforced to be embedded onto the last hidden state, and that is being propagated through the output generation, and everything about the input, the burden of compressing all the information about the input is put on one vector ht. You made that comment last time, right? So, which may not be a great idea. So, people saw this, that okay, this was happening, and to ensure that each of the output vectors at all time frames actually is looking at all the input time frames. They designed this algorithm, they came up with this idea called attention. What is the idea? Mathematically speaking, so this was h1, right? This was h1, h2 up to ht. They said tap all of these, okay, and add them with a particular linear combination and give all of these as an input to these things now. You understand? What we are saying is yt, okay, at every time now becomes a function of the previous y, of course, okay, and also a linear combination of all the hidden states of the input. You see what is being done here? So, you tap the hidden representations from each of the time steps in the input side, scale them with alpha 1s to alpha t, and all these alpha 1 to alpha t are learnable, okay, and then the output at every time step, make it a function of the previous output, of course, that we have done by architecture, also the linear combination of all the hidden states corresponding to the input side. So, now why was this made? This was made to ensure that the burden of carrying the information, all the information about the input is not laid only on the final hidden state, but you take into consideration all the hidden states of the input and take a linear combination of them and give it as an input to the output output LSTMs, right. And by the way, I gave a nomenclature also last time, right. This part is typically called the encoder and this part is called the decoder. So, this is the encoder decoder architecture where you take all the input tokens and compress it into a particular hidden state and then decode it, so to speak. Now, this is what is called as the attention mechanism, where you attend, to all the input hidden states. I'm only giving you a historical perspective of how this idea was arrived at. We will look at, the attention mechanism is very similar, attention mechanism that is used in a transformer is very similar to this idea, but it stems from this particular thing, that instead of burdening the last hidden state of carrying all the information about the input, you take an linear combination of all of the hidden states and give it as an input to all the outputs, is the attention mechanism. So, this idea was there. Then people thought, why do you even have an RNN? Because we know that RNNs are bogged with this problem of the vanishing gradient or exploding gradient, despite the fact that we have some hacks like the gating mechanism, etc., to ensure that it does not happen, but even then the long context was still an issue. So, people thought, why not do away with the recurrent architecture completely and come up with an architecture that only has attention. Now, after all, what is this attention doing? If you look at what this attention is doing, it is trying to capture the dependencies or the interactions between every token or every input time step through these alphas and h. Now, why not capture this completely using only the attention mechanism and completely do away with the recurrent architecture was the question. That is why the research article or the paper that introduced this architecture is titled as attention is all you need. So, what is not needed is that the recurrent architecture is not needed, all you need is attention. That is how they propose this idea. So, this is only a historical account of how and why the attention mechanism came. So, attention mechanism was not proposed by this transformer paper, the idea was there, this was what was called as attention, but now the contribution of that particular research article was that they completely got rid of the recurrent architecture and found out an architecture that can deal with the sequence data without even having parameter sharing across time and a recurrent architecture. Okay. So, this is only a historical account of why and how this thing was made. Now, let us look at the math of what the actual architecture is. Okay. So, now what are we given? So, we work with a single data point. So, given a data point x, so please note that this is a single data point which has t time steps. So, now every xi is a d-dimensional vector. This is what is actually called as a token in the literature typically. So, we have t tokens, which is one sequence, sequential data that we have. Now, the objective is to learn a projection or representation that encodes the interaction between the tokens. This is the goal. Now, given this data, learn a projection phi, okay, such that the output of this projection has to be in such a way that it tries to capture the interactions between every pair of token. So, that is what the goal is. Now, how do you accomplish this is the question. Now, start by representing, let capital X, okay, be a matrix which is in R T cross D having the data point. So, now what I do is that I take this data, see this entire data point that I have can be represented as a matrix, right, because every token is a d-dimensional vector, okay. I stack them all in a matrix and I get a T cross d-dimensional matrix, okay, which is a single data point, mind you. So, I have this single data point. Now, I want to learn a projection onto on this data point such that the interaction between every token is captured. That is my goal. Okay. Now, let us now first define linear projections of x using 3 matrices. Let us do that. Let us define a projection Q to be x times WQ, and this shall be, this we have T by D, and this will be D by DQ, and another projection x times WK and x times wv, where these three matrices these are learnable projections. Now, what am I doing is, see, please remember the goal. The goal is to learn a projection or a representation such that the interaction between the tokens are captured. That is what our goal is. So, towards that, first we will define three projections of this data, linear projections of this data x or a data point x via three learnable matrices wk, wq and wv. Is this okay? So, these for now these are simple, these are simply projections of data, okay, onto some linear subspace defined by wq, wk and wv. See, you all of you know that multiplying two matrices are equivalent to taking the vectors in the column of one matrix and projecting it onto the space spanned by the other, right. I am hoping that all of you know that. So, from that angle you take the data points and project onto the space spanned by the columns of wq, and same thing happens for all three, correct. Yeah. So, q, k and v are now three projections of data given by, our projection onto the space given by the columns of these three matrices, okay, that is what it is. Okay. Now, why are we doing this? We are doing this to get to the point where we learn a projection where the interactions are captured. Is that all right? Yeah. Okay. Now, for ease of understanding, right, let us say that dq, dk and dv are all same. Assume see, they need not be, in the most general treatment they need not be the same. I am avoiding writing three different symbols and just saying all of them are same, okay. So, let's assume these three are same. Now, okay, now please note that every row of these matrices, okay, corresponds to the projection of one token in the data. The way we have defined these matrices is that every row of this matrix is actually the projection of a token of data onto the space spanned by wq, isn't it? Why is that? Because look at this x. So, x has t rows, okay, and d columns. So, every row here is one token, and you take that row and multiply with this wq, which means that every row of q is projecting one token onto the space spanned by wq, correct. Okay. So, now let us define what is called as the attention vector. Okay. We will stop here and continue in the next lecture.